What occurred in example 1, part 2 is always true. If the inverse function of f of x is the inverse function of x, then f after the inverse function of x equals x, and the inverse function of f after f of x equals x. Doesn't matter what order we do this in, we will always end up with x. In words, if we perform a function after its inverse, or vice versa, its inverse after its function, then we always get back to where we started from. We always get back to x. This is often given as an alternative definition of an inverse function. Suppose f of x maps to y of x maps to f of x is a bijective function. Then the inverse function of y maps to x, is such that f after the inverse function of x equals x, and the inverse function of f after f of x equals x. So we'll always get back to x, no matter which order we do this in. If y equals f of x is a function, then the curve which represents the function consists of all points x comma y, which equals to x comma f of x. So x mapping to y consists of all the points x mapping to y. The inverse function, y equals the inverse function of x, will then contain all the points y comma x. So y mapping to x. From geometry, it can be shown that y comma x, so y mapping to x, is the image of the point x comma y, x mapping to y, under the reflection in the line y equals x. So this is the line y equals x. We should know this off by heart. We should be able to recognize it instantly. And it basically cuts through our x and y axis like a diagonal. So every point along that line is equal distance from the x-axis as is the y-axis. So for example, we have the point 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and so on. And then minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, and so on. Thus, to construct the curve which represents the inverse function y equals the inverse function of x, given the curve representing y equals f of x, we do these 4 steps. Step 1, draw the line y equals x. We may be given this line, but if not, we will need to know the scales on the axes. Part 2, note where this line intersects the curve of y equals f of x. If it does, these points will also be on the curve y equals the inverse function of x. Part 3, take a few more points on the curve y equals f of x and find their images under reflection in the line y equals x. Part 4, join these points up to form the curve y equals the inverse function of x. The line y equals x should be an axis of symmetry of the two curves. So if we have a look at our diagram here, here's our x-axis, here's our y-axis, and here's our line y equals x. So this is our function f of x, this curve here, and every point has been reflected in the xy axis. So we can see this point here is reflected down here, this point here is reflected down here, this point here is reflected down here, that point there is reflected down there, this point here is reflected down here, and so on. And eventually the two curves intersect. So we can see that the line y equals x is an axis of symmetry of the two curves. So we have the exact same image, a mirror image on the left of the line y equals x as we have on the right of y equals x. Example 2. The curve in the diagram opposite represents the function f of x maps to the square root of x. Defined on the domain, x is an element of R, the real number set, where x is greater or equal to 0. Part 1. Taking the codomain of f to be the set of non-negative real numbers, find an expression for the inverse function y equals the inverse function of x. So remember, these are our steps 1, 2, and 3. So in practice, the rule for the inverse function of x can be found from the rule for f of x by the following method. Step 1, write the given function as y equals f of x. So we're going to let y equal the square root of x. Part 2, rearrange this equation to get the x on its own. So if we have y equals the square root of x, to get the square root of x to just become an x, the square root goes over the equal sign and becomes squared. So we get y squared equals x. So we have x equals y squared, which equals the inverse function of y. And part 3, switch x and y, and this gives y equals the inverse function of x. So this x becomes y, this y becomes x, or x squared, and this y becomes x as well. So the inverse of y equals the square root of x is y equals x squared. Part 2, on the diagram, sketch the curve y equals the inverse function of x. So the curve y equals square root of x intersects the line y equals x at the points 0, 0 and 1, 1. So I'm going to draw on the line y equals x along here. And we can clearly see that the point 0, 0 is a point of intersection, as is the point 1, 1. One other point on this curve is 4, 2. And there's the point 4, 2. And its image is 2, 4. So we can clearly see that they are equal distance apart. So the point 4, 2 and the point 2, 4, they're a reflection of each other in the line y equals x. So the inverse function y equals x squared is shown opposite. So basically, if I join these points together, they end up forming this curve here, which is the inverse. So this is y equals x squared, and that is y equals the square root of x. So they are the inverse of each other. So if I was to join these points together, I would end up with y equals x squared, which is the inverse of my original function, y equals the square root of x. So we also have the points 9, 3 and 3, 9, 16, 4 and 4, 16, 5, 25 and 25, 5, 6, 36 and 6, 36, etc. They just don't fit on this graph. One thing to be careful about is that if the scales on the x and y axes are different, then the line joining a point and its image under reflection in the line y equals x does not appear to be at right angles to this line. So for example, if your x values went across in ones and maybe your y values went up in twos, so you would have 1, 2, 3, 4, dot, dot, dot on your x-axis, and then 2, 4, 6, 8 on your y-axis. Or maybe you might have 1, 2, 3, 4 on your x-axis, and 5, 10, 15, 20, and so on your y-axis. So if that is the case, then when you do draw on the line y equals x, it will not be a perfect diagonal through the x and y axis. So just be careful with your scales.